Asymmetric tensor fields enable model creation and data analysis for scientific domains such as fluid dynamics. Unlike symmetric tensors, asymmetric tensors have complex eigenvalues and eigenvectors. To allow in-depth analysis, this decomposition of the gradient tensor was introduced in 2009. Upon the decomposition into the real and complex domains, the eigenvector manifold contains 4 distinct regions: pure counterclockwise rotation and pure clockwise rotation in the complex domain, and anisotropic stretching, also called pure shear, in both the real and complex domains. For the gradient tensor field of the liquid flow field in this diesel engine, the existence of complex eigenvectors indicates the rotational component of the flow vector field is stronger than the pure shear component. Reversely, the existence of real eigenvectors indicates pure shear component is stronger than the rotational component. In 2012, the notion of eigenvector graph was introduced. Nodes are connected regions in the data that have the same eigenvector classification. Degenerate points are also considered as nodes in this graph. The edges in the graph indicate adjacency information between the regions. For degenerate points, their corresponding nodes are connected to their container regions, which must be complex domains. For eigenvalue manifold, we have the different regions: positive scaling, negative scaling, counterclockwise rotation, clockwise rotation, and anisotropic stretching. For the same slice of the diesel engine, we show the eigenvalue manifold. The eigenvalue graph also consists of nodes, each of which is a region of the same dominant behavior, and edges that record adjacency information. Here we note that there are often many regions in real-life data. We can inspect the data at different scales continuously. Furthermore, our work includes the identification of the set of atomic operations with which the graphs can be simplified, algorithms to realize these operations, and definition of scales that decides the order for these operations to be carried out. Now we describe our graph construction through the region extraction for surfaces. Given a tensor field defined on a surface of triangular mesh, we trace region boundaries. In eigenvalue manifold, there are junction points where 3 types of regions intersect. To have a better understanding of the dominant features from the asymmetric tensor field, we develop a multi-scale analysis of eigenvector and eigenvalue graphs. To enable the necessary analysis, we identify atomic operations for the simplification of these graphs. For eigenvalue graph, we have 3 additional atomic operations. Complexity metrics let us identify the operations that simplify our graphs, where cost of each simplification operation serves as a scale for our framework. This slide shows diesel engine simulation dataset at different scales. We can see significant amount of reduction in topological complexity through elimination of smaller features and degenerate points at higher scales. For this Sullivan vortex dataset and additional Gaussian noise, we demonstrate our multi-scale analysis to show the final scale contains the dominant features. Our system constructs the multi-scale analysis on the data in minutes, decided by the number of triangles in the mesh and the number of regions we have. After the analysis, we can save the analysis result to provide interactive study in the future.